Next, we have a look at the scattering from a delta function potential. We agreed upon that the delta function is a little bit abstract, but this will be very instructive because it is an exactly solvable problem. We see again how the delta function works in practice, and we learn more about boundary conditions. So this problem is set up with the following potential, which is very localized in space. So there is a very large potential at a certain point, and the potential vanishes everywhere else. Now the Schrödinger equation just looks like always in these one-dimensional settings, writing the derivatives with respect to position as these dashes, and then the potential energy. So this just looks like this. Now let's first have a look at the boundary conditions. It is instructive to integrate this equation over a small interval from minus epsilon to plus epsilon. So a little interval that contains the delta function. After all, the delta function is really defined in terms of a property involving an integral. So if we do this on the left-hand side, then we will basically get nothing when the interval is very small. So in the limit that epsilon goes to 0, this integral of e times psi just does not pick up much because the function will be finite and we have a very small interval. So for a very small interval, and indeed a vanishing size of that interval in the limit, we just obtain 0. On the left-hand side, we have these two terms here, and this one here is just a derivative, so we can evaluate it immediately. This simply becomes h bar squared divided by 2m times the integral of this piece here, and this will just convert the second derivative into a first derivative, which we will have to evaluate at these integration boundaries. And from this term here in the integral, we simply obtain the value at the position where the argument of the delta function vanishes. So what I've done here is to integrate this term here over this small interval. And so I just need to insert the value of this function at x equal to 0, which is included in this interval. So integrate over an interval that includes the place where the argument of the delta function vanishes. And in this term here, again, I integrated this piece here, and this just becomes the first derivative evaluated at these two different positions. So this just gives us these two terms. And now we see that this actually amounts to a boundary condition, because this left-hand side also has to be evaluated in this limit where epsilon is very small. This allows us then to solve the problem in the following way. First of all, let's agree again that we have two regions 1 and 2, and inside there we just have plane wave solutions. Again with some arbitrary coefficients. Just as written here. And again, K is related to the energy, basically by the de Broglie rule. Now the wave function has to be continuous at the place where the two regions meet. And this simply tells us that these coefficients just have to add up to the same value. But now looking at the other condition which we just derived, we see that the derivative of the wave function actually makes a jump. So when we look at this expression in particular here, this becomes the derivative of the wave function evaluated in region 2 minus the derivative of the wave function evaluated in region 1. And in the limit that epsilon goes to 0, this is still then just evaluated at 0. So from the condition above, this can be written in the following form. This jump of the derivative has to be proportional to the value of the wave function at this point, multiplied by this factor here. Now the wave function here can be evaluated in two different ways, either using the value in region 1 or in region 2, because both of them are identical. So I'm going to evaluate them using the values in region 1. This then gives me the following expression. So now we have two conditions for four coefficients, a1, b1, a2, and b2. And so we have again some freedom to look at interesting solutions. In this case, I want to show you how to exploit the symmetries of the problem, because the potential is clearly symmetric when we reflect it in space, and this can be used to simplify our solution. In particular, we will find two different types of solutions. Let us start with the so-called symmetric solutions. For this, we say that the amplitude of the particle to move to the right in region 1 should be the same as for moving to the left in region 2. So we say that b2 has to be equal to a1. And we say the same for the amplitudes in the opposite direction. So a2 has to be the same as b1. Now this automatically satisfies this condition here. The sum of these two coefficients will be the same as the sum of these two coefficients. And this expression here now simplifies as follows. So we can now use this to isolate b1 and express it in terms of a1. These two coefficients will be proportional to each other because this is a linear system of simultaneous equations. And we solve it by isolating b1 on one side and a1 on the other side, and then just divide by whatever is in front of b1. Well, what will be in front of b1 when I move it to the right-hand side? Well, there will be 2ik minus 2m gamma divided by h bar squared. And in front of a1 on the left-hand side, I will also have 2ik, but now plus 2m gamma divided by h bar squared. So this is one possible solution, and it is actually a very interesting one. First of all, at positive energies, which is really what we were assuming so far, this will simply be a symmetric wave function which smoothly meets at the place of the delta function and then oscillates symmetrically on both sides of this potential and displays a kink at this position, which is simply proportional to the value of the wave function at this point. But secondly, something very interesting also happens at negative energies. In that case, our exponential functions become increasing and decreasing function, and we will have to rule out the coefficients appearing in front of a1 and b2 because they will become functions that decay in the wrong direction, where kappa will now be defined with a negative sign in front of the energy. So a1 has to be 0, and then it seems that b1 has to be 0 as well. But there is one exception, because this term here could be infinitely large. And indeed, if one takes these limits in the correct way, one finds that this is an allowed solution, and this simply corresponds to a bound state. So the condition for this bound state is 2ik equals to 2m gamma divided by h bar squared. The 2 of course cancels, and this one here now becomes minus kappa. And this is a positive number, so we find that this bound state exists if gamma is negative. So this is a delta function, an infinitely large spike of a potential, but pointing downwards. So the delta function then really looks like a potential like this. And in there we can find one solution which has some exponential decay into both directions. Well, we can also find an antisymmetric solution. Where we say that A2 is equal to minus B1 and B2 is equal to minus A1. But this turns out to be much more boring, because in this case we find from our first condition that A1 plus B1 has to be the same as minus A1 plus B1. But this means that this value, of course, has to vanish, but this is the value of the wave function at 0, evaluated either in region 1 or in region 2. So this has now to vanish. But the difference of the derivatives and the second condition was proportional to this value. So this difference now vanishes and the wave function does not have a kink. Indeed, we see that the wave function now vanishes exactly at the position of the delta function. So this simply becomes a sine function with some arbitrary amplitude a along all space. So both in regions 1 and 2, including the position 0 where the delta function is located. So now we have two independent solutions, and let me denote them as psi s for symmetric and psi a for antisymmetric. In the first solution, I'm going to set this coefficient a1 to 1 just for convenience. So I have e to the I kx, and then I have the coefficient b1, and this will just become this term, which I'm going to denote as f. And this is how it looks like in region 1, and in region 2 it is just propagating into the opposite direction. So it will look like this in region 2. And the antisymmetric solution is really just a sine function everywhere, but we can write it like this in region 1, and it will just look like the same, of course, now in region 2. And again, I chose a suitable value for the overall amplitude. And now these are two independent solutions, so this can be used to find all the solutions by superposition. And this includes the solutions that we use to calculate reflection and transmission probabilities. So for instance, we can just sum these two solutions, and then we get a solution which just has this component with an amplitude 2 on the left-hand side of the barrier. So this is an incoming wave of a certain amplitude 2. And we also have the sum of these terms here. So we have a solution which is being reflected, and this will have the amplitude f minus 1. And on the other side, we have only a transmitted wave because these two terms here cancel, and the amplitude is just 1 plus f. So now we can read off the reflection and transmission amplitudes directly. The reflection amplitude will just be the ratio between these two amplitudes here. So this will just be f minus 1. And the transmission amplitude will be the ratio between this coefficient and again the incoming amplitude. So this will be f plus 1 divided by 2. Now we can of course also look at the difference of these solutions, and then we simply obtain the solution with the particle arriving from the other side, being either reflected or transmitted. So this will again result in an amplitude 2 here, f plus 1 here, and f minus 1 here. And so now we get reflection and transmission amplitudes from the other side, which we would generally denote by R prime and T prime. But they here just take the exact same values, which is not a surprise because the problem is really symmetric under this reflection, which we exploited when we found the solution. Now we have constructed some very specific solutions, but in order to construct the most general solution, it is convenient to introduce the so-called scattering matrix. This is denoted as S and collects all this data into a single mathematical object, namely a 2x2 matrix, which has the entries as given here. So this is a 2x2 matrix, and what this does is to relate the amplitudes of the incoming particle from either side, so either A1 or B2, to the amplitudes of the particle moving away from the scattering region, so B1 and A2. So this simply gives us these coefficients, B1 and A2, by a matrix multiplication with these coefficients here. And this then gives us our most general solution. And now this is a very fascinating matrix, and I will discuss it in some more detail in the next segment, but let's write it down for this particular case. So for the delta function barrier, this now just takes the following form. Now for this specific problem here, the scattering matrix has three useful properties that already illustrate why this is a useful object. And the first one is just to realize that this scattering matrix is a symmetric matrix. So when we transpose it, then the matrix just remains the same, and this is simply because these two off-diagonal elements are identical. And secondly, when we multiply the scattering matrix with its Hermitian conjugate, we just obtain the identity matrix. So let me briefly work this out. So the scattering matrix itself is just as given. Now the Hermitian conjugate means that we take a transposition and a complex conjugation, but the transposition here does not make any difference because the matrix is symmetric. So we just need to multiply by the complex conjugate of this matrix. Hence we have the complex conjugate of this quantity f in here. And now we can work this all out. Now we are going to use that f is a complex number of length 1, which you can see simply from its definition because it's a complex number divided by its complex conjugate. Okay, so let's do these matrix multiplications. So this times this one here, this will be the absolute value of f squared minus 2 times the real part of f. There will be an f and an f complex conjugate, which I just added with this minus sign, and then plus 1. All of this will be multiplied by 1/4 because we have these terms 1/2 everywhere. So this is multiplying this term with this term, and then we have to multiply this term with this term. So there we get again plus f squared, but now plus 2 times the real part of f plus 1. And this is the very first entry in there. Now this one here is 1. This is 1. These two terms cancel. And here we have other ones. And together with this 1/4, we just get 1 in here. So now I worked out the top left element of this matrix. And of course, this took a lot of space, so I just made some space for the next matrix element, which we obtain by multiplying these two numbers here in the row with these two numbers in the second column. And there we now find again an f multiplied by a f complex conjugate. So let me directly write down 1. And then we have some other terms, which I'm just going to write down. There will be minus f complex conjugate plus f minus 1. So these are just the 4 terms for multiplying out everything which we have here and here. And then we get 4 terms multiplying everything here with this one here. And this gives us another 1. Now plus f complex conjugate minus f minus 1. And now you see that this actually vanishes. So all these 1's cancel and all these terms appear with opposite sign. So this simply becomes 0. Now when we work out the other 2 matrix elements, we get exactly the same expressions. It's exactly the same combinations of numbers. Now we can cancel these factors 4 and we just get the identity matrix as I mentioned here. And finally there is one property which is related to the bound state. When we calculate the scattering matrix at the energy of the bound state, then f actually diverges, so you can say the scattering matrix becomes infinitely large. So now these are some specific properties of the scattering matrix in this particular setting, the scattering from a delta function, but they also carry over to other problems, as I'm going to discuss in the next segment.